Welcome back, everyone. Renewable power is growing faster than any transmission system can adapt. Every nation producing wind and solar energy faces the same technical wall, and that is how to store electricity when nature rests. Engineers around the world are exploring new forms of mechanical storage that work with gravity itself. Instead of relying on chemical reactions, these systems lift and lower enormous masses, converting electricity into potential energy and back again. Among the most promising of these innovations are gravity-based energy towers and deep shaft storage facilities now being built across Europe, North America, and parts of Asia. To understand the concept, picture an electric motor winding up a heavy weight suspended by steel cables inside a vertical shaft. When excess electricity is available, the motor lifts the mass, storing energy as gravitational potential. When power is needed, the weight is released and spins generators as it descends. It's actually the same principle used in hydroelectric dams, but without the need for water or reservoirs. The energy storage capacity depends on three factors: the total mass, the vertical distance moved, and gravitational acceleration. Multiply these, and you get the stored joules, which engineers can translate into kilowatt hours for practical comparison. The origins of this idea stretch back to early experiments in mechanical storage, but only recently have materials, sensors, and power electronics become precise enough for large-scale use. Switzerland's Energy Vault built one of the first demonstration towers using concrete blocks stacked and lowered by robotic cranes. Each block weighs roughly 35 tons, and the tower can shift thousands of them automatically in response to grid signals. Similar designs are being adapted in Italy, Germany, and Canada, where engineers are improving accuracy and reducing mechanical wear through advanced control software and magnetic coupling. In Germany, a company called Gravitricity is testing a different layout. Instead of a tall tower, it uses deep vertical shafts originally created for mining. Heavy weights travel along steel guide rails, lifted and lowered by winches at the surface. The mine shaft approach allows greater height differences, sometimes hundreds of meters, and thus more stored energy. Old industrial infrastructure is reused instead of abandoned, turning disused mines into living components of national energy systems. Engineers in Poland, the United Kingdom, and Finland are evaluating similar conversions, comparing the long-term maintenance costs to traditional battery farms. Energy efficiency is a key advantage. In most prototypes, round-trip efficiency, which is the amount of electricity recovered after a full charge and discharge cycle, ranges between 75 and 85%. That figure rivals lithium-ion grid batteries, but without degradation even after thousands of cycles. The main limitation is response time. Batteries can respond in milliseconds, while gravity systems take seconds. For frequency regulation and long-duration storage, however, the response is more than sufficient. Operators can schedule lifts and drops based on weather forecasts, creating stability for wind farms and solar plants that fluctuate throughout the day. Material science plays a central role in improving these systems. Early towers used standard reinforced concrete blocks. Today, engineers are experimenting with composite masses made from recycled steel, basalt fiber, or even packed soil encased in polymer shells. Each material has unique density, cost, and wear properties. The challenge is finding a balance between mass, durability, and handling speed. The hoisting cables are often made from high-strength synthetic fibers that resist stretching, ensuring consistent tension and minimal friction loss. Advanced bearings and magnetic damping reduce mechanical noise and extend system lifetime to more than 30 years. Control systems have evolved as well. Modern gravity storage relies on digital twins, real-time software replicas of each tower, to monitor cable tension, temperature, and alignment. Artificial intelligence algorithms predict mechanical fatigue and adjust movement profiles to extend component life. In Italy and South Korea, engineers are integrating these models directly into national grid management software. When demand spikes, the towers discharge automatically in coordination with wind and hydro assets. The result is a stable frequency that supports electric vehicles, data centers, and urban transit without sudden voltage drops. One of the most impressive applications is the hybrid tower configuration under development in Spain. Instead of a single central shaft, multiple counterweights move independently along a cylindrical frame. Each unit is driven by its own motor generator, allowing finer control and partial loads. If one mechanism fails, others continue operating. This modular redundancy reduces downtime and improves dispatch reliability. Spain's design also includes heat recovery from braking systems, converting frictional energy into electricity or district heating. It is a showcase of how mechanical and thermal systems can merge into unified storage platforms. Environmental impact is another area of research. Unlike pumped hydro, gravity towers require minimal land and no water reservoirs. They can be built on industrial sites, near substations, or even integrated into tall buildings. Architects in the Netherlands are studying facade-mounted counterweights that could stabilize small local grids in dense urban districts. Similarly, engineers in Japan are testing subterranean systems designed to operate silently beneath city streets. The minimal footprint and low environmental risk make gravity-based systems suitable for regions where traditional hydro storage or chemical batteries are impractical. Cost remains the greatest obstacle to widespread deployment. Early units cost between $2 and $3 million per megawatt of capacity, more than lithium-ion alternatives. Yet analysts expect costs to fall sharply as steel and construction methods are standardized. In the United States, several energy cooperatives are evaluating multi-site procurement strategies that share logistics and assembly costs. The European Union is funding cross-border projects linking gravity towers to renewable clusters in Italy, Poland and France. These shared deployments aim to prove the economies of scale that could make mechanical storage competitive by 2028. Another promising direction involves hybridization with existing energy assets. In Indonesia, planners are exploring whether gravity storage can be combined with geothermal plants to absorb surplus nighttime generation. By lifting weights during low-demand hours and releasing them during peaks, operators smooth out production curves without touching the turbines themselves. Similarly, Canadian hydropower stations are being tested with gravity modules that assist in rapid balancing when reservoir levels are low. The underlying engineering principle is identical. Use mechanical potential as an elastic buffer that reinforces other energy sources rather than competing with them. Let's break down the core energy equation in practical terms. The potential energy stored in a mass equals its weight, multiplied by the height difference. A single 35-ton block lifted 100 meters stores about 9.6 megajoules, or roughly 2.7 kilowatt-hours. Multiply this by hundreds or thousands of blocks, and the numbers become meaningful for industrial scale. A tower 150 meters tall with 5,000 tons of moving mass can provide several megawatt-hours of storage, enough to stabilize a medium-sized wind farm. The precision control software coordinates each movement, so that the generated power matches the grid's frequency exactly. Safety systems are essential. Engineers design multiple braking layers, including mechanical clutches, regenerative braking through the generator, and emergency fail-safes that clamp the load instantly if power is lost. Each block's motion is tracked by LiDAR sensors and redundant encoders, ensuring centimeter-level accuracy. Tests conducted in Switzerland showed that even under simulated cable failure, the block stopped within half a meter of prediction. This level of reliability is crucial if these systems are to be built near populated areas. National certification standards are being drafted to regulate construction, maintenance, and operational control of such energy towers. Noise reduction and aesthetics also influence public acceptance. In France and Portugal, projects near residential zones use soundproofing panels and visual cladding to blend with the skyline. Some experimental towers even double as architectural landmarks, with lighting effects synchronized to energy flow. Public tours and educational displays explain how gravity becomes electricity, helping local communities appreciate the visible infrastructure of clean power. These human-centered design elements may seem secondary, but experience shows that public perception often determines whether a technology expands or stalls after its first installations. Scaling from prototype to national networks involves both engineering and policy. Grid operators must certify that gravity-based systems can participate in ancillary service markets, frequency regulation, capacity reserves, and peak shaving. Italy and Germany have already drafted frameworks allowing mechanical storage to earn the same compensation as battery systems. In North America, transmission operators are still updating standards to include them. Once integrated, gravity towers can act as distributed nodes, charging automatically when renewable supply is high and discharging during demand spikes. This software-based dispatch makes them part of the intelligent grid emerging across the developed world. One emerging variation uses underground chambers rather than towers. The principle is inverted. Massive pistons pressurize air in sealed caverns when lowered, then release that pressure to drive turbines as they rise. By combining gravitational and pneumatic effects, engineers achieve higher energy densities. Pilot plants in Finland and the United States are evaluating whether these gravity compressors can serve as short-term energy buffers for microgrids. If proven viable, they would expand the application of gravity storage beyond large towers into compact underground installations suitable for urban or remote environments alike. The international race to commercialize gravity energy storage mirrors what happened with wind and solar about 2 decades ago. Early investors focused on proof-of-concept sites, but now national energy ministries are adding mechanical storage to their strategic roadmaps. By 2029, at least a dozen large-scale systems are expected to be operational across Europe, with expansion also planned in South Korea and Canada. Analysts project that if costs reach $1 million per megawatt-hour of installed capacity, gravity storage could capture 10% of the global stationary storage market by the end of the decade. That is a realistic and measurable target. Critics sometimes question why we should invest in mechanical storage when chemical batteries already exist. The answer lies in life cycle and resource independence. Gravity systems use steel, concrete, and software, not rare metals or electrolytes. They require minimal recycling, contain no flammable materials, and function for decades with simple mechanical upkeep. This makes them especially valuable for countries with limited access to lithium or cobalt supply chains. A mix of storage technologies ensures resilience in the energy system, protecting nations from raw material volatility while supporting renewable integration year after year. The education sector has begun to recognize this potential. Technical universities in France, Poland, and the United States are including gravity energy storage modules in engineering curricula. Students learn to calculate potential energy, design load-bearing components, and simulate grid interactions. These programs ensure that when the industry expands, a trained workforce is ready. Collaborative projects link universities with national laboratories and startups, accelerating innovation through open data exchange. The resulting ecosystem mirrors how aerospace or semiconductor fields matured through steady refinement rather than sudden leaps. Future versions of these systems will likely combine artificial intelligence, magnetically levitated masses, and adaptive gearing that adjusts to daily grid cycles. By eliminating friction and optimizing acceleration curves, they could achieve efficiencies above 90%. Engineers are already experimenting with supercapacitor-assisted lifts that handle small fluctuations, instantly leaving the main tower for slower, high-capacity movements. This hybridization of fast and slow storage within one mechanical framework could redefine how grids maintain stability, blending classical physics with modern automation in a single elegant design. The story of gravity-based energy towers is ultimately about rediscovering simplicity. By turning motion into storage, engineers have created a technology that can last for generations with minimal environmental impact. From Swiss valleys to Indonesian geothermal fields, from Canadian mining towns to coastal Portugal, the same principle holds true. Energy can be held in place, waiting patiently for its moment to return. As nations race toward reliable power without compromise, these silent vertical megabatteries may become the backbone of a new balanced energy era. Thank you very much for watching. Please like and subscribe.